Everyone. Thank you for joining us today for Minitab's Boost the Bottom Line by Eliminating Waste with Quality Tools webinar. My name is Stacy McDaniel and I'm a Marketing Content Manager here at Minitab. A few housekeeping notes before we begin. We will have a Q&A session after this presentation, so please submit any questions you have and we will do our best to answer them. We recommend viewing this webinar via laptop or PC for best results. If you experience a delay or sync issues with the audio and slides, please exit the webinar and rejoin or refresh the page. We will send a copy of the recording following the webinar, so there's no problem if you miss anything or would like to review afterwards. I'd like to introduce our presenter today, Rob Lievense. Rob is a solutions architect at Minitab, matching solutions to the technical needs of large organizations. Rob has more than 25 years of experience in data-driven approaches to improvement in both commercial and government organizations, has presented at several conferences and published several papers along with a book. We're so excited to have Rob present today's webinar. And with that, I'll hand it over to Rob to begin today's presentation.
Thank you so much, Stacy, and welcome. When you talk about quality tools, there's several in Minitab, and I think what comes to mind in most people is that these are for compliance or they're for monitoring. But what you didn't know is that often a quality tool can lead to a strategic improvement that adds tremendous value to an organization. The story that I'm telling you today actually happened, so this is based on real events. It's been changed a little bit because I want to protect the organization where this came from. But the gist of the story is the same. And our story takes place at a facility using high-speed packaging lines for consumer goods. Now, the output of these packaging lines would be multiple these cartons, these kind of glued cartons that include multiple light inner vacuum form packaging with product. So there's 10 lines in this facility, and there were dynamic check weighers added at some point. And the goal of the dynamic check weighers is every single carton goes across it at high speed, and is to ensure that the correct amount of product was put into the carton. There's millions of cartons packaged per week, actually maybe even per day. And then downstream, they get placed into case packs, they get palletized, and they eventually get shipped to distribution centers for the end customers. Now, the process engineering group of this organization is already assembling a capital request to update to state-of-the-art check weighers on all lines. However, the units are expensive, and we're talking somewhere in the neighborhood, this is a while ago, but it was about $150,000 installed for each of the 10 lines. Now, it's very common if you go out to this packaging area that there would be bins, and imagine a bin's about the size of a dorm refrigerator, and they would collect kickoffs from the check weighers regularly, and then they would rotate, put an empty bin in, they would bring these full bins back to a rework station where inner packaging was removed and placed back into the carton or feed magazines to be repackaged. And this is a fairly regular occurrence. Now, let me give you an idea about the measurement device, because we're actually going to be talking about measurement systems analysis. So we have this device, it's in line. You have a high-speed conveyor that brings cartons in over on your left. It goes across a stage in the middle of the equipment where the measurement is taking place, and the operators or technicians on the line are going to set up the control interface. Now, if it doesn't meet the low or the high, if it's not within the control elements that they enter, it gets kicked off with the pneumatic kicker and it goes into the reject bin. Anything that doesn't get kicked off goes out to the good cartons and the output. So I want to change gears here, and let's imagine we're executives and we're going to be taking a look at the results of how things are going. So this is good operations, and the executives are able to take a look at the dashboard. They can kind of see how things are going for this organization. And one of the things they notice is their efficiency that they measure in OEE is doing poorly. They want it to be over 80%. It's a high-speed packaging line. They have lots of volume. It's not where they need it to be. When we go over to the top right in the center here, we see order attainment, and this is the customer's order and how much are they actually able to ship, and they're only at about 82% of order attainment. They want to be 90 or above, so they're definitely not there. And there's all kinds of out of control points, especially on the low end. They're not so worried about the ones that are doing really well, but the ones that are really low, not great. They're doing a poor job. They need to do better. On the end here, they're looking at inventory turns on an annualized basis. They would like 25 or better. And you can see from a capability standpoint, long-term capability, they should be 1.33 or better, and they're not. So they're hurting there as well. When we look at the process availability, 20% of their process availability is eaten up in unplanned downtime. That is not great for this type of operation. They need every minute they can. And so they're also hurting. Well, now clockwise, when we get to the bottom, excess kickoffs make up the biggest quality incident that they've had for the period. So the biggest number. And keep in mind, it's regularly known that they're going to have a fair amount of kickoffs. This is when they have so many kickoffs, they have to stop the line. They usually have to isolate product, do some AQL sorting or AQL testing. They have to get the maintenance people over there, reset the equipment. So it's a big deal when they have a quality incident that involves excess kickoffs. What does this do? What this does is it makes them kick off a new project. They need to make an improvement. They can't wait to replace these units. So engineering, we have a cross-functional project. We need to fix this problem. And by the way, when we talk about new equipment, one of the first things that came up when we were scoping out this problem was, well, what's so bad about the old equipment that will be fixed with the new equipment? And that could not be answered. So our next step was, we need to look at this measurement system, because this online checkware is a measurement system. Well, good measurement systems, we know, need to be accurate, which means if you have a known quantity and you measure it over the system you're testing, you should get the same results. And you're going to get a little off due to just simple random variability, but it should be pretty close. That measurement system needs to be precise. So if I take the same object, run it over this checkware multiple times, I should get similar results. And then we also need this to be stable. I need to get these good results, the good accuracy, the good precision over time. Now, there are different ways to qualify a device. The first, and I would say maybe the highest level, are technical and engineering specs. Now, these are important mostly for making sure that whatever measurement device you're using fits the application that you're measuring. In other words, you want to make sure the span of measurement equals what you're trying to measure. But they really don't do very much for identifying if that system is working well. The next one, calibration, I used to hear this a lot. Well, you know, the device is calibrated. We calibrate it every 6 months. Calibration is a snapshot. Really, all it's doing is you take a very controlled procedure, usually in very controlled situation. You can see this person has gloves on. And you have some standards. In this case, he's got standard blocks and he's checking a caliper. And you're checking how close that measurement is of that device to that standard known measurement. Now, this is important. You definitely need to center your device, but it doesn't tell the whole story. The gold standard, you can see I have a gold star at the bottom, is measurement systems analysis. And this is where you're studying your measurement system, ideally in the environment where it's used and with the people that are going to use it. It doesn't do any good to study a measurement system in a laboratory environment with engineers. It really needs to be where it's used. Now you can see the little picture here. We actually in Minitab have developed recently a measurement systems analysis module. So if you have folks that are doing a lot of this work, this could be very helpful because it gets right into the meat of doing measurement systems analysis without having to navigate through any screens. So let's talk about measurement systems analysis. Gauge R&R is one type of measurement systems analysis. There are multiple, but we're going to use the one that is a simple type study where you're looking for repeatability and reproducibility. You have to know this before you can rely on those measurements. First question would be, is there enough resolution in your equipment? Also, is there variation between operator to operator? And how much of your total tolerance are you using in your measurement system? You really need to be able to trust that system before collecting data to solve a problem. And the problem that we have is making sure that we have adequate product running down the line. And our system doesn't seem to be doing a very good job of that. And to get a little bit deeper, what is repeatability? What is reproducibility? So if I take that same object, same person, measure it multiple times, that's the variation within the operator. We call that repeatability. Now, if you have multiple people using that same device on those objects and you're comparing operators, that's variation between the operators. And if you're thinking statistically, we are going to use a type of analysis of variance where you're basically comparing your variation within to your variation between. And one last thing to talk about is bias. This is where if you have a measurement that is consistently too high or too low, now calibration does help somewhat with bias, but it also can be due to if you're studying a system and you're using non-random trials, you can actually end up with having a bias measurement device. You also may have some technical limitations of the device. Sometimes methods can create bias, how you are holding objects, how you are tightening jaws and clamps, those types of things, those can have an effect on bias. And, those humans, every time we get humans involved, things can go sideways a little bit. So good procedures, good training can help minimize bias. The best way to minimize bias, or at least identify it, is to use tools within our gauge studies, material or measurement systems analysis, and that can help you design a good system. So we're going to talk a little about design, and I will be showing you this in Minitab here shortly. Design is extremely important when you're doing measurement systems analysis. Often I see goofy results. If I've ever been called in and there's goofy results, it's because maybe some of these considerations weren't met. The first one that might seem a little odd for a statistician to say is the samples or the parts that you use. And I say parts because in default, Minitab uses the term parts for your objects that you're measuring. They should not be chosen at random. They should be engineered to represent the entire measurement spectrum of interest. Now, what do I mean by that? Well, we want to be able to know that a system can do a good job of measuring parts that are within specifications as well as outside of specifications. So a good rule of thumb is to grab a couple parts that are right in the sweet zone, right in the center of your specification range. Grab a couple of parts that are close to your low specification. Grab a couple of parts that are close to your high specification. And then add a couple parts that are below your low specification. I would say minimum 20% below. and a couple of parts that are 20% above your high specification. Now, if you happen to look, these points, 2, 4, 6, 8, 10, they add to 10 parts. Well, guess what? The default when you're doing an MSA, any kind of gauge R&R in Minitab is 10 parts. So works out well. Now, to get these parts or these objects, it can be some doing to get them done. And sometimes you need to do controlled process adjustments. So you need to make sure that you've controlled the output, that it's not going to go to regular production, and you make adjustments to get those out of spec and in spec samples. You may have to go through reject bins and good part bins to also find them. Or there have been times when we've actually had to engineer samples. I remember when we did a really tight tolerance deep draw stamping for a spark plug in an organization one time, and they actually had to send samples to the machine shop to have them artificially changed. So they turned some of them down, they welded and turned some other ones to make them large to get the range of samples that they needed that represent that whole spectrum of good and bad parts that we can expect. Now, you always want to make sure those samples are clearly labeled, make sure they're very controlled, so they're not going to get into good production. And you have to make sure they're going to withstand the handling required to measure multiple times. If not, that is a destructive gauge R&R or destructive measurement systems analysis. That's a more complicated thing to get into. You can call Minitab tech support, or you can look out in our documentation and get an idea of how to do that if you're faced with that challenge. I will not be covering destructive gauge R&Rs today. And the last point, you've gone to this trouble getting these samples, labeling them, making sure they're what you need. It's also really good practice to go the extra mile and try to have these samples measured with an instrument that's known to be highly accurate, more accurate than what you're testing. So maybe a coordinate measuring machine, maybe some kind of lab instrumentation. That gives you standard measures for the samples, and that can be really helpful if you do bias studies later. Sometimes it's not possible, but if you can do that, make sure you do it. Now randomness comes in. You can't have a discussion with a statistician without talking about randomness. The trials of how you measure these samples must be randomized to get good results. So you basically have to make sure that every subject, every one of those parts of that population has an equal chance of being chosen when you're sampling for doing your measurement. So it's kind of like application of statistics to samples that are not chosen at random is like a surgeon working behind their back. You could get a good result, but not very likely. We're going to transfer over to Minitab now so I can kind of show you how this is done. In our stat menu, we have quality tools, and right smack dab in the middle would be gauge studies. And we're going to start out with a design so we have the ability to create a gauge R&R study worksheet. And this would be the default. Starts out with 10 parts, 3 operators, and 3 replicates. Well, in our situation, remember, we have an auto feed to the equipment. So there really is no operator. It presents the carton to the conveyor the same way every single time. So we're actually going to go down to 1 operator. The machine is itself an operator. Well, statisticians were involved in this study, and we said, you know what? If we're saving some time on studying operators, well, we can just bump up our replicates and get an even better estimation of our gauge error, our measurement error. So we ended up doing 5 replicates. Now you could do some options on, how you want to randomize. Now we randomized within operators, but I only have 1 operator, so it doesn't really matter. I highly suggest to run this in a randomized fashion because you don't want to do this in order. And the reason being is, you might get better as you measure. So if you keep these in part order, maybe the early parts might have more error or more variability than later parts. It's also possible there's fatigue. You know, after you get to the fifth part, you start getting fatigued. So it could be the opposite. So we need to mix those up. And when we do that in Minitab, you can see that these are all mixed up within the 5 trials that we're doing. Okay, so that's optimum. That's what we want. Now here's some actual data. And we added a couple things. We've got all the weights that were added, but also we just wanted to identify the trials because we passed each carton through 5 times and we randomized within the trials. Well, actually, this one is not randomized. No, it is. It is. It's randomized. Yep. And then products were identified. We had 3 different types of products that ran on the lines. We had small cartons, we had medium cartons, and we had large cartons. So we used 0, 1, and 2. Just in the data, we didn't want to make any mistakes. Now that we have data, we can analyze it. So we go out into Stat, Quality Tools, Gauge Study, and we're using the simplest, which, well, I guess, excuse me. Let me get back in here. The simplest would be a type 1 gauge study. Oops, sorry about that. But we used a crossed gauge study. There are other styles. Sorry about that. Okay, I think we're back to normal here. There could be a nested study. That would be if you have multiple operators and you can't measure all parts for all operators, or an expanded study. Often that would be for like laboratory measurements where you have more than just operators. You might have multiple preps, you might have multiple ovens, you know, other things. But we're using the crossed. Now we just need to put the part numbers and the measurements in here. I don't have to worry about operators because I don't have any. So it's actually a gauge R study, to be technical. And then we can actually put the information on the gauge that we're studying in here. That's very helpful. And we can run the study. So I'm going to go to the one that I've already run here just so we've got it. Now it's going to give us a warning. It says, oh, by the way, I didn't see any operator values, so we're omitting that from the analysis, and that was appropriate for this study. And all this is telling us up front is that, yes, we have a difference between the carton to carton and the variability and repeatability. So this doesn't tell us that much in the ANOVA table. The variance components are more interesting. We can see that we had 24 grams of total variation for small cartons, and the variability because of repeatability, in this case it would be like gauge error, is only roughly 3 thousandths of a gram. Not going to lose any sleep over that. Overall, our error, our study variation is only 1%. And that gives us 134 distinct categories. And what that means is you want the most distinct categories you can get. So remember I talked about the spectrum of measurement, and that's from the lowest out of spec part to the highest out of spec part and all the specifications in between. I can break up that span in 134 different categories. That means I have 134 chances to detect a part is different from another part. So you want that as big as you can get. So this small carton actually performed very, very well. Almost all my variation is due to the parts that I knew were going to vary because I picked them to be different. I can see that I have very low range between the 5 samples of each part. So that looks awesome. And there's so little variation within these groups that it doesn't even show up as I'm plotting the averages. And the X bar chart, what this is telling me, when you're usually doing statistical process control, you want your points within your limits. It's opposite for doing a gauge study. This is telling me I have very good signal compared to the random error that I have that's represented by my control limit. So this one's an excellent gauge. But look what happened when we did the medium, which is the bigger container. Ooh, now 25 grams of variation, 2.5 grams is due to repeatability. So about just under 10%. Only 4 distinct categories. So not good. Very difficult to tell in-spec parts from out-of-spec parts when I only have 4 categories. And I can see that my study variation is a pretty good percentage of the part-to-part variation. It shows up, especially in this plot, where you can see we have some pretty good spread about those 5 trials we did with each part. And over here, our random error, our random variation, is much larger than what we saw in the small part. So we don't have as strong a signal coming from that measurement system. Large is even worse. We actually, out of 510 grams, now these are much larger packs than the other 2. It's kind of a giant bonus pack. That's why the scale is so much bigger. Out of 510 grams, 333 is due to repeatability. So I only have 1 distinct category. My gauge R&R is 81% of my study variation. So it's even greater. It's going to take into, the reason these don't total up is some of your part-to-part variation is going to show up here. But horrible, just a horrible result. And we can see these are bigger than the part-to-part variation. I have so much spread, I can't really even tell the average differences between my parts, maybe just 1. And we can see that over here. So I can only tell this part from all the rest. That's not good. So this was a very similar result for all 10 of the devices out there. Well, what happened? We got all this information. We realized that these check weighers were not doing what we hoped that they were doing. They weren't doing a very good job of protecting the right amount of product. So we went in from an engineering perspective and looked into the capabilities of the equipment, looked at the operations manuals of the equipment. And what we found out was the check weighter is not a scale. It does a dynamic calculation. So it takes into consideration the mass of the object moving across the stage, the volume or size of the object, and the speed, how fast are you running it? And it calculates what the measurement would be based on those 3 parameters. Well, because you have 3 parameters, the device needs to be trained when you do a major change in size or weight or line speed. And so there's a training sequence where you run 10 parts over it, and then you kind of have it adjust itself to those parts before you actually use it for measurement. Now, the equipment was added to the packaging lines back in the late 90s. And at the time, each line was running dedicated large lots of product. Well, that's not the way that the operation was running in modern times. In modern times, the current practices required scheduling many small lots per week, and that was pushed by customer demand. So every unit on the floor was not dedicated, it was running multiple products. So what we finally figured out is that the units were probably trained in a lot of cases to the small, whichever the best performing MSA was, that's probably where it was last trained. But we had no way of fixing that. Well, we did, but we didn't know about it. The other thing that we found out was there was a low cost, about a $10,000 annual maintenance plan for the equipment involving biannual inspections and repairs. And for whatever reason, even though it was a really cheap maintenance agreement, it was discontinued as a cost savings. And that was important because you've got hot glue, you've got dust, dirt, and they would come in twice a year, clean it all up, replace worn parts, lubricate it, make sure it was in top running condition. And they were specialists. They knew more than our maintenance people did. So that was reinstituted right away. And when we look at, we did a 5 whys in our Engage solution. And the big thing, this is not normally the case when we have a problem, but this was a procedural problem. We didn't have to buy any new equipment. We didn't have to do any really engineering fixes. We had to just update the operating procedures. And what we did was we separated the products into families so we could tell where a major change was. And we did some gauge studies to make sure we were not creating error. And then the new procedure was anytime the line was set up with a major change, they would be required to retrain the equipment. So let's see what that did to our results. So we'll get our small one. And I'm going to split this view. Well, remember I said this was the last thing that was trained. So we didn't see huge differences. I mean, we dropped a few of the categories, but that's probably just some random variation. Probably if we retrained it again, we'd pick that up again. But by and large, the small cartons were weighed very effectively. It didn't affect this one because this was probably where the equipment was trained in the beginning. But when we look at the medium, that was a very poor performer. And we compare the two, the variance components. We went from about almost 10% of contribution in variance components down to 0.03%. The percent of the study variation due to error, which is repeatability, went from 31% down to less than 2%. And we gained from 4 distinct categories up to 88. So we made this equipment just from making sure it was trained to the package that it was being run after a major change. We dramatically improved its performance. And much the same happened with our large, which remember was really bad. So we went from 65.5% contribution to variance components of basically gauge error, repeatability error, down to 0.26. The study variation went from 81% down to about 5%. And we gained distinct categories. We went from 1 to 27. So not as big a gain on the medium, but keep in mind there's a lot more stuff in the large carton. So we didn't expect that we were going to get as good a result as we did with the medium, but it's still much, much more serviceable. Now, we also wanted to compare and say, well, did we really make an improvement? And this is something that I think statisticians like to do. So what we ended up doing was we did a test for equal variances, and I'm just going to pick the one that we know we had, major differences, or it looked like we did. So when we compare these cartons post to pre, you can see all the variation that we had before we retrained with our new procedure, and now we look at the variation that we have today. So we actually shared this with the executive sponsors to be able to prove that, no, we made a huge improvement. So if you didn't understand all the stats in the gauge R&R, you look at this chart, it makes sense. Wow, you went from this much variation down to this much variation. That was a huge improvement. And also from a bias standpoint, we can see that we were able on the post, once we trained it, our average bias was very small, basically zero. So we were measuring pretty close to zero. And, this is going to exacerbate, you got to look at the units here. I mean, we're only going from 0.2 negative to 0.2 positive grams. It tends to be the heavier packages. You have this pattern, you go from underweighting to overweighting, but it's so small, it was practically irrelevant. So we didn't even bother. We didn't worry about the bias. It was set up very, very well. So the implementation of the procedure, it took a little while to get everybody on this same page, get everybody trained, get all the equipment maintained and up to the best shape it could be, and kick off new procedures across the whole facility. But once we did, we kind of monitored how things went for 6 weeks. We had one excess kickoff event that happened in that 6 weeks. And believe you me, it was an all hands on deck, because there were a few naysayers who say, see, I told you you wouldn't fix this thing. But when it was investigated, what was found out is the supplier of the printed carton ran out of the lighter board stock, substituted a heavier board stock with small cartons, and didn't get prior approval. So there was so much more added cardboard in the carton that it threw things off. And so that was kind of funny that we were able to find that. And I call that, lowering the water to find the rocks. We actually found there were other problems that were being covered over by having a imprecise measurement system out there that we were able to fix. Also looked at the supply of cartons prior to the improvement and after. And when that was annualized, people were shocked that it was $1.5 million of cartons that came from the rework area and ended up having to get thrown away. Now that's the tip of the iceberg in the value of this, because we had so many people dealing with it. We had to pay to have these scrap cartons hauled away. Also, through the ordering process, remember, we talked about ordering, we talked about inventory turns, through that, out the window, because you had to always order way more cartons than you needed because of rework. It ended up the rework stations that were kind of a permanent fixture on the packaging lines, they were all removed because what we found out is there were so few kickoffs in the bins, like a handful, that it was just more cost effective to just scrap the small number of kickoffs instead of pulling them apart and reworking them. And we were talking very, very few. They actually reduced the size of the kickoff bins too. Now the new check weighers, there were a few areas. We found that the large product was right on the fringe of the technical specifications of the units that we had out there. And it was a fairly new product. So there were a couple areas where we decided to buy some new check weighers as an organization, just because it, from a technical standpoint, it fit the product a lot better. So, but they didn't have to go all 10. So we had, I think, 1 or 2 that in our MSA studies, we just never could get them to perform as well as we'd like. And those, we only replaced like 2 or 3 of them instead of 10. the operational improvement, or OEE, the efficiency, got into the mid-80s for most of the weeks after the improvement. Now, it wasn't the magic bullet. There were still other issues, but this was a very huge issue, and it really affected efficiency. And we basically eliminated a ton of rework and a ton of problems. Order attainment increased about 89% with improved stability, so we didn't have those big swings. There were still some things that needed to be worked on, but it really did bump up our order attainment percentage. And unplanned downtime was below 15% by getting rid of this problem. So it had a really nice effect across the whole organization. Now, a great way to cap and to track a project like this would be in Engage. That's one of a Minitab solution. And I just wanted to show you that when you go out there and you look at completed projects, all of the information that was done can get captured. So you can have all of your R&R studies, you can have your 5 whys, and it's all captured in one place. So this would be a wonderful place to be able to capture all that information and maybe duplicate it across an organization. So this was a great project. We were able to use a relatively simple quality tool, and we didn't have to go into any modeling per se, or really any statistics, because the difference was so huge, going from such a big problem basically to almost no problem. It didn't take a rocket scientist, it didn't take statistics to show that we made a significant improvement. So I hope that you've enjoyed this story, and I'm going to move over to Stacy so we can close her off.
Thanks, Rob. We hope you all enjoyed the presentation. Please submit any questions you'd like answered today in the Q&A box now. We also ask that you provide your valuable feedback by taking the survey, accessible from the pink survey box at the bottom of this window. While we wait for some more questions to come in, I'd like to share some information about Minitab Insights Global Conference. If you enjoyed today's webinar and want to see more presentations like this one, please join us as we come together for the Minitab Insights 2023 Global Conference. Our conference will take place in person from May 1st to May 3rd in beautiful Scottsdale, Arizona. You'll have the chance to connect with innovators, peers, and professionals who help shape the future with data-driven insights and explore new solutions you can implement immediately. Now we'll get to your questions. Let's see. Okay, Rob, here's some questions. The first one is, how does repeatability and reproducibility relate?
So they're kind of additive to each other. That's why they're separate terms. So repeatability is when the same object, same person is measuring multiple times. And that was basically what we did in this study, because we didn't have operators. It's equally important to know that if I measure something and Christine measures something and Bill measures something, do I get the same results? Often, in my experience, that can be a case. We used to do a lot of engineered check fixtures, and that was usually the problem, is when multiple people tried it, they would maybe put the clamps on tighter, or they would work faster than the other one, putting in an indicator faster than another one and not letting it kind of settle out. So that's often a problem. So you need to be able to get that operator side balanced out so everybody measures the same. And then usually you can handle, okay, now how do we make it more repeatable? Repeatable is usually methods a lot of times, or I would say methods a lot, or clamping, to make sure that I can get something in the same location every time. And that's why, like, sometimes when you see calipers, it's more accurate to put them in a stand instead of having them held in your hand, because you can present that part the same way every time. And that those types of things usually improve repeatability. So I hope I answered your question.
Okay, next question here is, why is the tolerance not used for the R&R study while samples are collected with respect to TOL?
So I didn't show, we do have tolerance, and actually I can pull that up. I did have some of these with tolerance included. So you can, when you do set up your study, this is a great question. When you do set up your study, in the options, you can put your tolerance in here. And it's important. I think a lot of times what I used to do is run the study just on its own, to just take a look at the overall variance components and look at overall performance, and then reflect it back to percent tolerance. Now we can see this has horrible percent tolerance. So my total gauge error is 236% of the tolerance I'm trying to measure. And remember, I only had 4 categories. This was abysmal. And you might laugh and say, well, that's so bad. I can't believe that you used it. Well, they did. And whenever this was usually, if it was this bad, it was going to be a quality incident, because there were so many rejects. They had to get maintenance over, they had to get the technicians over, and they would eventually kind of try to readjust the checkware to get it to run better after the fact. But percent tolerance is important because it reflects how you're going to use the gauge and what you're trying to measure. Hopefully that answered your question.
Yeah, we actually had a few questions along those lines, so hopefully you answered all those questions. Next question, have you done this type of analysis with healthcare data?
Ooh, that's a fantastic question. I'm trying to think of the application to healthcare data. Are we talking about, I would say you could. We did it with laboratory instruments that were very similar to what you would use for healthcare data, where maybe you're doing some kind of preps and you're putting those preps into an instrument, and I'm thinking of like a hospital laboratory. What I will say is this: I think using these types of tools for laboratory instruments in both healthcare, pharmaceuticals, biologics, I think we're in the edge of a new frontier, because I think there's been other methods that have been used to define intermediate precision and some other things that have not been as effective as using a true measurement systems analysis technique. I have a friend of mine that still works with some laboratory people, and they've been retesting a lot of their instruments with gauge R&R or MSA type studies, and carrying them, looking back at the original qualification of the procedure and the instrument, and finding that there's a lot more error than that they thought there was in that device. So I think it can be very applicable. It's just the tough thing is it's maybe not something that they think about today, but I think it can really help you improve the precision of those instruments.
Thanks, Rob. Daryl clarified that he wants to measure weights of patients in beds. So that's his medical healthcare question that you just answered.
Oh, that would be perfect. I mean, we've done all kinds of scales. So yeah, you could do it on weights. The thing that gets a little tricky, and you can call tech support, is you might have a tough time repeating with the same patient, because you don't want to create fatigue. Whenever you're studying people, there's always a lot of things we have to consider. So it might be more of a nested study or a specialized study, just so you're dealing with human beings, and you don't want to kind of overly stress them, unless you're using like fake weights to check it. But if you're actually using actual people, I would say just have to be careful. There are methods to do that, but you make sure that you check with the boards that you need to, that what you're doing is within the bounds of appropriate treatment.
Great. And we have time for couple more questions. The next one is, please explain how number of distinct categories relates to your MSA outcome or predictive power.
Sure. So the goal when you are testing, any kind of measurement system, I want to be able to define the difference between a part that's within specification and a part that's outside of specification. The more distinct categories I have allows me to be more finite. I can tell the difference between, one that's 3 clicks away from low spec as opposed to 1 click. So if you think of it almost like a histogram, you can change the binning of a histogram so you have one big graph, so it's not very sensitive, or you can change the binning so you have a lot. So it's how many of those bars can I fit within and outside of my specification so I can tell the difference. And that gets really important when you're making parts that are very close to spec, because if you don't have many categories, you might have a part that's 10% over spec, but your measurement system, because you lack distinct categories, says, oh no, this is good. So I think the more that you can get, the better. I don't know if there's a magic number for the amount of distinct categories you want. There's usually more magic numbers by looking at the percent tolerance or the percent of study variation than there are necessarily distinct categories, but they're very related.
Thanks, Rob. Okay, this will be our last question, and just for the other questions that didn't get answered, we will try to respond via email and let you know. The last question is, for executive reviews, can you assign a dollar amount per every percent point of variation?
Oh, wow, that's a good one. Now, I'm assuming percent point in variation when it relates to measurement error. That might be tough to do directly, but I would say in a study like this, if we wanted to dig a little bit further, we probably could find a relationship between, how much error is there in an instrument, and then relate it back to how much scrap was generated or how much rework was generated. Now, the engineering team didn't dig that far, and that was a little frustrating because we didn't even have records on how much product was being reworked, which kind of blew my mind. They just kind of assumed, oh, this is just a normal part of the process. It would have been nice to have that data. And I think if we knew the quantity of product that was reworked, we could go back to how much error that we detected in the instrument for that particular size carton and probably have some kind of relationship that could equate that back to dollars. But I think it would take some work to try to join that together. But I would say it's something that could be done.
Thank you, Rob. Now, to close this webinar, I'd like to share some information for those who may not be as familiar with Minitab. For 50 years, Minitab has helped companies spot trends, solve problems, and discover valuable insights in their data. In the webinar today, you saw the quality tools available within Minitab statistical software. Some of our other solutions include Minitab Engage, which you saw, Minitab Connect, which you saw, Minitab Workspace, Minitab Model Ops, Real-Time SPC, Education Hub, and SPM. We also offer training, statistical consulting, and technical support services. Thank you all for attending today, and we hope you found this webinar valuable. We'll keep the webcast on for a few minutes to give you more time to fill out the survey. Thank you for your time.